Welcome. In this video, we're going to look at complex numbers and Euler's formula. Let's start by stating Euler's formula. Euler says the complex exponential e to the j theta equals cosine theta plus j sine theta. Now we need to show that this makes sense, that is, that e to the j theta behaves like an exponential. We're just going to assume that for this video. In the next video, we'll go through the proofs. For now, we'll just accept two facts. One, the law of exponents holds. That is, e to the j alpha plus beta equals e to the j alpha times e to the j beta. And two, the complex exponential differentiates as we'd expect. That is to say, d by d theta e to the j theta equals j e to the j theta. As I said, for now we'll accept these facts. We'll prove them in the next video. Let's look at some very simple but important examples. Starting, e to the j pi over 2 equals, well, we put pi over 2 in the right-hand side of Euler's formula, and we get cosine pi over 2 plus j times sine pi over 2. Well, cosine of pi over 2 is 0, sine of pi over 2 is 1, so this simply equals j. Next formula, e to the j pi equals, we'll plug this in, cosine of pi plus j sine of pi. Now, cosine of pi is minus 1, sine of pi is 0, so we just get minus 1. This leads to the following fun formula. We have e to the j pi plus 1. I move the minus 1 over to the left-hand side, and I get equals 0. We have the remarkable formula that contains e, pi, j, 1, and 0, all in one simple relation. All right, let's compute two more of these exponentials. E to the j times 2 pi equals, I won't write down cosine and sine, I'll just do the substitution. Cosine of 2 pi is 1 plus j times sine of 2 pi is 0. So we get 1. Let's do one last one, which is a little more complex. We'll do root 2 times e to the j pi over 4. Well, this is root 2 times what we get from Euler's formula. Cosine of pi over 4 is 1 over root 2 plus j times sine pi over 4, which is also 1 over root 2. So we end up with 1 plus j. These are fun formulas, but what makes Euler's formula useful is its relation to polar coordinates, which we'll get to on the next slide. Now we'll combine Euler's formula with polar coordinates. Let's approach it this way. Start with our complex number z equals x plus jy, and we'll let r and theta be the polar coordinates. I'll abbreviate the word coordinates. What this means is z equals x plus jy equals r cosine theta, that's x, plus j r sine theta, that's y. Let's manipulate this a bit. This gives us r times cosine theta plus j sine theta. And now we see Euler's formula sitting right there. Cosine theta plus j sine theta is e to the j theta, so we have is r e to the j theta. Let's put these near each other in one formula below. Z equals x plus jy equals r e to the j theta. In terms of coordinates, we have here a complex number, x plus jy. we'll call Cartesian or rectangular coordinates. And r e to the j theta we'll call polar coordinates or polar form. This is a great formula. Let's redo the examples we saw in the previous slide, and then we'll look at some further more complicated examples. I've prepared this slide with the two ways of writing z in rectangular and polar form, and with a set of axes for the complex plane. Now let's look at our examples. First one was e to the j pi over 2. Now we're not going to compute it using Euler's formula. We're going to consider it as polar coordinates with r equals 1 and theta equals pi over 2. That's r e to the j theta. So what I do is I go to my plane, I draw my unit circle, that's radius r equals 1. Polar coordinates tells me to go to this unit circle, follow it around pi over 2 radians. That lands me right here on the y-axis. Unit distance, which means j. So e to the j pi over 2 equals j, which we knew. Next one, let's do e to the j pi. That has, again, r equals 1. This time, theta equals pi. So in polar coordinates, it says go to the unit circle, start at 1, follow the unit circle around pi radians. That lands us on the negative x-axis, right at minus 1. And so this complex exponential equals minus 1. Let's do e to the j 2 pi. Well, again, r equals 1. Theta this time equals 2 pi in polar coordinates. And so that says start at 1, follow the unit circle around 2 pi radians. That's one whole circuit. We end up right back at 1. And therefore, this equals 1. Now let's do the example where r wasn't 1. That was root 2 e to the j pi over 4. This says r equals root 2 and theta equals pi over 4. Graphically, this says go to the circle of radius root 2. We'll put that out about here. Here we'll draw that circle. Follow this circle around pi over 4 radians. That's right there. We'll draw the ray at pi over 4 radians. That looks like this. They intersect right here. This, of course, is the line y equals x. So we're on the circle of radius root 2, and on the line y equals x. This equals 1 plus j. In the next slide, we'll look at interpreting what multiplication means by thinking of it in terms of polar coordinates. We'll do the example j times z by writing it in polar form. So writing j in polar form, we have e to the j pi over 2. And writing z in polar form, we'll just use general polar coordinates, r e to the j theta. Multiplying this out using the law of exponents, we have r e to the j times theta plus pi over 2. What we see is that multiplication by j leaves the magnitude of z unchanged, that is, it was r before and r after, and adds pi over 2 to the angle of z. That is, it rotates z by pi over 2. What happens if we multiply by an arbitrary e to the j alpha times z? Well, in polar coordinates, that's e to the j alpha times r e to the j theta, which is r e to the j theta plus alpha. In other words, leaves the magnitude unchanged and it adds alpha to the angle of z. Finally, let's do arbitrary multiplication and division using polar coordinates. We'll take an arbitrary number z, and we can write it in polar form as r1 e to the j theta 1, and an arbitrary number z2, which we can write as r2 e to the j theta 2, perfectly arbitrary r1 and r2. If we multiply these two things together, we get z1 times z2 equals. I won't write it out, but see what you get. You get r1 times r2. Those are the magnitudes multiplying. Then when you multiply the exponentials, the law of exponents gets us j theta 1 plus theta 2. Lengths multiply. And angles add. That's the theta 1 plus theta 2. Division looks quite similar. If I take the two numbers and I divide them, I have z1 over z2 equals r1 e to the j theta 1 over r2 e to the j theta 2, which is r1 over r2. And now the rules of exponents say that's j of theta 1 minus theta 2. We conclude that the lengths divide, that is the ratio of r1 and r2, and the angles, you get a difference, theta 1 minus theta 2. In summary, use polar coordinates for multiplication and division. Use rectangular coordinates for addition and subtraction.